A fully loaded 747 weighs up to 412,000 kilograms. It hits the runway at roughly 270 kilometers per hour. Every kilogram of that weight, every kilometer per hour of that speed, arrives through 6 tires, each one about the size of a washing machine. Those tires don't explode. They don't visibly compress. They don't crack or shred or leave a trail of rubber down the runway. They just take it, and then they do it again, 500 times, sometimes more, before anyone replaces them. A car tire runs at around 2.5 bar of pressure. An airplane tire runs at 14 to 16 bar. That's 6 times higher, roughly the pressure found inside a fire hose mid-use. So the first question isn't why they survive the impact. The first question is why they don't burst just sitting on the tarmac. Then, what material handles going from 0 to 270 kilometers per hour in under half a second without tearing itself apart? Why are these tires inflated with something other than air? And if something does go wrong, how bad does it actually get? Most people, when they think about airplane tires, imagine something like a car tire but bigger, thicker walls, more rubber, basically a tougher version of something familiar. That instinct is wrong in almost every direction. Airplane tires are not thick-walled. They are not soft or heavily padded. They don't work by absorbing the landing the way a cushion absorbs a fall. A thick, stiff tire would shatter on impact at those speeds. The force would have nowhere to go, and the structure would crack. The actual solution is the opposite. Airplane tires are engineered to flex, but in a very specific, controlled way. And that distinction between absorbing force and passing it along correctly is what the whole design is built around. Here's what an airplane tire actually does. It doesn't take the weight of the aircraft. The landing gear struts do that. Those hydraulic legs that compress on touchdown and then slowly extend again. What the tire does is far more specific. It grips the runway, it spins up from 0 to ground speed in about half a second, and it holds its shape under 14 to 16 bar of internal pressure, while all of that is happening simultaneously. 3 violent forces arrive at once on landing: the full downward weight of the aircraft, the horizontal shear force as the tire goes from stationary to 270 kilometers per hour in an instant, and the heat generated when rubber meets runway at that speed. The tire has to handle all 3 at the same time, not absorb them, handle them, meaning redirect, distribute, and survive them. This is the part everyone misses. The rubber in a tire is not the structural part. The rubber is the envelope. The actual strength of the tire comes from layers of nylon cord running through it, called plies, woven at specific angles, typically 30 to 45 degrees relative to the direction the tire rolls. Think of it like the weave of a bullet-resistant vest. A single cord can be cut easily. Hundreds of them crossed at angles, under tension, distribute any force that arrives across the entire structure. No single point takes the full hit. The force spreads. That's why an airplane tire can hold 16 bar without ballooning outward. The cords are under so much tension they physically resist expansion. The rubber just fills the gaps and makes it airtight. But here's where it gets crazy. That controlled flexing, which is the whole point, the thing that stops the tire from shattering, generates heat. Every time the tire compresses and rebounds under load, the cord layers slide microscopically against each other and create friction. On landing, that process happens extremely fast. The contact patch, the part of the tire actually touching the runway, can hit temperatures above 200 degrees Celsius in seconds. Hot enough to degrade rubber, hot enough to weaken the cord structure over time. Therefore, every element of the tire's design is also a heat management strategy, which is why airplane tires are not inflated with air. They use nitrogen, pure nitrogen. Air is roughly 78% nitrogen already, so the pressure numbers work out the same. But the other 21% of air is oxygen, and at high temperatures, oxygen reacts with rubber and accelerates its breakdown. Oxygen also makes fire more likely. In a tire interior that routinely hits 200 degrees Celsius, that's not an abstract concern. Nitrogen is inert. It doesn't react with rubber. It doesn't support combustion. It also holds its pressure more consistently across temperature swings, from negative 50 degrees Celsius at cruising altitude to over 200 degrees on landing, because nitrogen expands and contracts more predictably than a mixed gas. The tire you see on a parked aircraft in a cold morning gate will be inflated to essentially the same pressure when it touches down in a hot desert 3 hours later. That consistency matters when the margin between safe and dangerous is narrow. Now here's the surprise. The high pressure itself is protective, not dangerous. This seems backwards, but the geometry explains it. A higher pressure tire is stiffer. A stiffer tire has a smaller contact patch, the area of rubber actually touching the runway. A smaller contact patch means less rubber is flexing at any given moment. Less flexing means less heat generated per landing. So running at 16 bar instead of, say, 8 bar doesn't make the tire more likely to burst. It actually reduces the internal stress cycle that would wear the tire out. The pressure is the protection. The smoke on touchdown confirms this. Every hard commercial landing produces a puff of white smoke from the main gear tires. Passengers sometimes think something has gone wrong. Nothing has. The tire goes from stationary to 270 kilometers per hour in half a second. And in that moment, the outer surface of the tire is moving slower than the aircraft. It hasn't fully spun up yet. The friction between rubber and runway burns off a thin layer of tread. That layer is designed to vaporize. It's a calculated sacrifice. The outer millimeter of rubber ablates away, so the structural cords beneath don't overheat. The smoke is the system working. Compare this to an F1 racing tire and the differences are stark. An F1 tire runs at around 1.2 bar, barely more than a bicycle tire, and about a 1/13 of aircraft pressure. F1 tires are soft by design because softness creates grip. They heat up fast and wear fast. A set might last 30 laps. An aircraft tire runs at 16 bar because hardness creates structural survival. It's designed to last 500 landings. An F1 tire is engineered to give everything it has in 40 minutes. An aircraft tire is engineered to perform identically on landing 499 as it did on landing 1. These are almost opposite philosophies, sharing the same basic shape. A car tire is an even worse comparison point. A car tire is designed for continuous rolling at moderate loads over long distances. Its sidewalls are tall and soft to absorb road imperfections. That's the ride comfort you feel. An aircraft tire has almost no sidewall to speak of, a much narrower cross-section and cords running at angles tuned for sudden extreme loading rather than gradual fatigue. A car tire hitting a pothole at 100 kilometers per hour is stressed. An aircraft tire hitting a runway at 270 kilometers per hour is doing its job. The history of aircraft tires begins in a place that looks nothing like aviation. In 1903, the Wright brothers' Flyer at Kitty Hawk ran on modified bicycle inner tubes, literally. The same type of tube a cyclist would use, adapted to carry a 340-kilogram aircraft for the first time in history. It worked barely for a 12-second flight at low speed. The tube was never designed for what it was asked to do, but nothing else existed. By World War II, aircraft had grown enormously in weight and speed, and tire technology was struggling to keep up. One version of the history, and documentation here is sparse, so treat this cautiously, holds that rubber shortages during the war became so severe that American engineers experimented with tires partly made from reclaimed materials, including rubber from discarded golf balls. The rubber from roughly 100 golf balls revulcanized and layered into the carcass of a single tire. Some accounts say the program ran briefly before the tires began delaminating under flight stress, and the idea was abandoned. Whether the details are exactly right or embellished over retelling, the underlying truth is solid. Wartime material constraints pushed tire engineers into genuinely strange places. The modern high-pressure nitrogen-filled design didn't appear until the jet age of the 1950s. Jets doubled aircraft weight and landing speed within a single decade. The tires that existed couldn't handle it. Michelin and Goodyear effectively had to invent a new category. They developed bias ply construction, those chord layers at diagonal angles, specifically to survive jet speed touchdowns. The resulting design was so effective that its core principles haven't fundamentally changed in 70 years. Concorde, which landed at speeds exceeding 300 kilometers per hour, faster than almost any other commercial aircraft before or since, required a completely different rubber compound for its outer tread, developed specifically for that aircraft and never used on anything else. One version of the record suggests Concorde's tires failed repeatedly in early testing under the combined stress of extreme speed and the heat generated by its long runway runs. The final compound that solved the problem was, by several accounts, proprietary and never disclosed. It was retired with the aircraft in 2003. The Space Shuttle sits at the far end of the spectrum. Its main landing gear tires were inflated to 21 bar, higher than any commercial aircraft, and were replaced after a single landing. One landing, that's it. The tire was structurally intact after touchdown, but the engineering margin was gone. The stress of one shuttle landing consumed the entire design life of the tire. the most expensive single-use tire in the history of flight. Aircraft tires are retreaded up to 7 times before the carcass is condemned. The same retread process used on long-haul trucks. Strip the worn outer layer, bond a new tread, cure it under heat and pressure. Works on aircraft tires with the same structural result. A legally certified retread is required to perform identically to a new tire. Airlines use them regularly. Nobody on the aircraft knows. Tires that have reached their maximum landing cycle count, removed from service before they've failed simply because the rules say they're done, are sold to drag racing teams. Drag racers specifically seek out retired aircraft tires and run them at lower pressures, exploiting the enormous structural safety margin built into the aviation specification. A tire that's too old for a passenger aircraft still has significant life for a drag strip. When a plane sits at a gate for hours, the tire develops a flat spot where the contact patch presses into the concrete under the aircraft's static weight. Engineers call this cold set. The flat spot rounds out within the first few seconds of taxiing as the rubber warms and the structure returns to its original shape. It's built in, tolerated, and not considered a defect. The heat fuse plugs embedded in aircraft wheel rims work on the same principle as the fuse in a home circuit breaker. They're made from a low melting point alloy. If brake heat after a rejected takeoff builds past a certain threshold, the plugs melt first and deflate the tire in a controlled way, releasing pressure before the tire can burst. Intentional designed failure to prevent the catastrophic version. Tire pressure is checked by hand before every single flight. A maintenance engineer with a pressure gauge, pressing it to the valve stem, reading the number. No automated system. The check that stands between a multi-hundred-million-dollar aircraft and rolling out on a flat tire is a human being with a handheld tool that costs less than a round of drinks. Michelin and Goodyear supply tires to most of the world's commercial fleet. The global aviation network, carrying billions of passengers a year, depends on production from a relatively small number of manufacturing facilities. A significant disruption at one, a fire, a prolonged strike, can ripple into aircraft groundings within weeks. The supply chain is tighter than most people would expect for something this critical. The chord angles in aircraft tire plies distribute point load force across the whole structure. The same physics used in body armor. A stab-resistant vest works because diagonal fibers redirect force laterally rather than letting it pass straight through. A tire cord at 45 degrees does the same thing when the runway hits. The mechanism that stops a knife and the mechanism that survives a landing aren't as different as they look. Fighter jet tires routinely handle touchdown speeds above 500 kilometers per hour. Carrier-based aircraft add the shock of an arrestor wire catch, the aircraft going from 250 kilometers per hour to 0 in about 2 seconds. Same carcass construction principles as a commercial tire, pushed to roughly double the performance envelope. The margin is engineered in, just higher. Now, the real trade-off. The system has one failure mode it hasn't fully solved, a rejected takeoff at high speed. When a pilot aborts a takeoff at maximum speed and stands on the brakes, the carbon brake discs can exceed 1,000 degrees Celsius. That's hot enough to glow orange. The heat fuse plugs are designed to release before the tires burst, but the window between fuse activates safely and tire ruptures first is narrow. In a small number of documented incidents, the tire has failed before the fuse had time to respond. The aircraft survived, the engineering held at the system level, but the specific part didn't behave as designed. The industry response is active thermal monitoring. Brake temperature sensors now feed real-time data to cockpit displays. Pilots can watch the temperature rising and make better decisions about cooling time before a second takeoff attempt. The sensor doesn't change the physics. It gives the crew the information to manage them. Here's how the tire itself is changing. Michelin has developed a radial construction for aircraft tires. The same shift that happened in car tires decades ago, where chord layers run perpendicular to the direction of travel rather than at a bias angle. Radial construction reduces flex cycle heat generation by roughly 30%. The Airbus A320neo family has been transitioning to radial tires since around 2019. Airlines using them report measurable reductions in replacement frequency. The bias ply design that Michelin and Goodyear invented in the 1950s to survive the jet age may be approaching the end of its dominance. Longer term, electric and hydrogen-powered aircraft will land lighter and at different thermal profiles than current jets. Some engineers project that future short-haul electric aircraft could use lower-pressure radial tires, converging after a long arc, back towards something closer to car tire physics. Not the same, but using some of the same principles for the first time in jet aviation history. The next time the wheels come down and the runway rises up, 2 seconds before the thud, 6 tires spinning from 0 to 270 kilometers per hour in half a second. Designed smoke, cord layers holding 16 bar against the runway's impact. Nitrogen staying inert where oxygen would react. Fuse plugs on standby. The reason it feels like nothing is that the engineering is so good you were never meant to notice it working. That's the whole point.